Once we get the hang of it, calculating these gravitational potential energies is kind of just a plug and a chug. I'll doodle a little picture so we can get a visual on it. We just have to get the right equation and plug the numbers in. One little thing is, in these big gravity equations, the R that we use is always the distance from the center to the center. So the radius that we're going to plug into our equation is the height of, in this case, the bowling ball, and the radius of the Earth. The height of the bowling ball was 400 kilometers. That means 400,000 meters. The radius of the Earth is a 6.37 number. You don't have to memorize that. You can always look it up. When we add those two together, 400,000, 6,370,000, the 4 kind of lines up with the 3. So this turns into 6.77 times 10 to the 6 meters. Now that we've got that, we can just sort of plug it into our gravity equation. After our little proof, our calculus proof, the gravity equation is negative GMM over R. For this first one, I'm going to put all the units in just so you can see how they work out. G has got the units of newtons, meters squared per kilogram squared. The mass of the Earth is 597 times 10 to the 24 in kilograms. And then our bowling ball is 5 kilograms. Divide all that by the R value, which was the new math, 6.77 times 10 to the 6, and that's a number in meters. When we crank this out, the ball up in orbit, just checking my calculator, it's a negative value. Oops. It's a negative value, and I got it to be 2.9 times 10 to the 8. Unit-wise, this meters cancels with one of those meters, and these kilograms cancel with those 2 kilograms. So we end up with the units of newtons times meters, which, as we talked about in grade 11, that's equivalent to a joule. So we get a great big negative number. One way to think about it is that even though it's 400 kilometers above the Earth, it's still trapped. That bowling ball is going to take a lot of energy added to get it to escape Earth.